fiber orientation from intracardiac maps using physics-informed neural networks. So thank you, Francisco, and please go ahead.
Yeah, so my name is Francisco SAHLI COSTABAL. In Chile, we use two last names, so it's a bit confusing.
Yeah, sorry.
No problem. Yeah, it happens all the time. Yeah, so today I'm going to talk about how we can learn the fiber orientations based on electroanatomical maps data. This is a big collaboration with a couple of groups that you can see the names in this slide. So I think we have already seen the motivation to study this. I mean, this is a conference about the heart, so I don't think I need to motivate much why we need to study this. But the idea here is that we want to create patient-specific models to evaluate treatments. For example, ablation strategies, just like Ali showed, where you can evaluate whether pulmonary vein isolation works or not. And for this, we would like to create patient-specific models. So so instead of using generic models, we would like to tailor them to a specific patient, so we can make a specific predictions for that patient and see if a treatment will work or not. So we can get the anatomy from medical images, but there are many other model parameters that we don't know beforehand, that are basically fiber orientations, if you have fibrosis or slow conducting zones, and basically we don't know what's the conductivity tensor for our electrophysiology simulations. So we would like to tackle this problem in this work. So just a basic reminder of how activation times are measured in cardiac electrophysiology. So we have a traveling wave in the atria, for example. This is a left atria, a very simplified traveling wave, and a physician goes in with a catheter and places it there and records an electrogram, and from that we can measure at what time the traveling wave arrived. So the idea is that we would like to create something like this, an activation map, where basically I know at every point at which time the electrical wave arrived. And this is widely used in clinics. It can be done minimally invasive, and we think we can extract a lot of information from this data. So the approach that we took here is to use physics-informed neural networks. And first, I'm going to explain an approach where we just use an isotropic version, where we just estimated the conduction velocity, and then I'm going to explain how we got the fibers. But the idea here is that we will create a neural network that predicts the activation times in space. So here the input will be a coordinate in space in the atria, and the output will be an activation time. And we will train this network to satisfy the data available, which is what the physician measured with the catheter, basically all the activation times. But we also will create a neural network that predicts the conduction velocity depending on space. And for this, and to link these two, we will use a model which links the conduction velocity to the activation times, which in our case is the aconal equation, which we know should be satisfied for this kind of traveling waves. And we also add some regularization terms. So to put this more formally, we know that the activation time satisfies the aconal equation. So in this case, it's just an isotropic aconal equation. So then we rewrite this equation in a residual form. And then we say that the activation times and the conduction velocities are represented by neural networks. And we also make the conduction velocity to be bounded between 0 and a maximum conduction velocity. and because we know it cannot be negative, and for physiological ranges it cannot be above certain values. And then we train the neural network to minimize this loss function, which has this data fidelity term, minimizes the residual of the PDE, in our case the diagonal equation. And we also add a total variation regularization term for the conduction velocity, and also some terms to regularize the neural network. And if we do this in the atrial surface, we penalize the conduction, the propagation of the wave two corners, but they have two different conduction velocities. So red will be a slower conducting zone, and blue will be a faster conducting zone. And we train different methods. So we train our approach, which is here, physics-informed neural network, against a regular neural network that doesn't know about the physics of the problem, a Gaussian process, which has also been proposed to be used to interpolate activation times, and what I think is mostly used currently, which is just a linear interpolation between the activation times. So you can see here that with our approach, we can approximate this discontinuity here. We can capture that, and really struggle, especially here in the corners. They tend to go to values that are very unrealistic because we don't have any data there. So now, if we make a cut through this line, through this diagonal line, and take a look at the results, we see that the two neural networks actually perform really well, estimating the activation times here in blue. But the physics-informed neural network captures really well this step change in conduction velocity, and the other methods really struggle with that. So yeah, we also took this to 3 dimensions, and we also apply some uncertainty quantification, and with that we can also do active learning, which basically means that we can also tell the physician where to put the catheter to get the most information out of it. And I will not go into all the details, but just to show you that we can adaptively sample the atria just to get the best reconstruction, with the fewer amount of samples. And if you're interested in that, we can discuss it later. And now you could tell me, but we know that the electrical propagation in the atria is not isotropic, which we knew from the beginning there was a limitation, and now we have extended this to an anisotropic case, so we can learn the fibers. So we start with the anisotropic eikonal equation, which is very similar to the previous one. The only thing is that we have replaced the conduction velocity now by a tensor that represents the conduction velocity. And so we use a couple of facts to simplify this problem a little bit. So we use that D is a symmetric tensor, and so we reduce the independent components that we need to estimate from 9 to 6, and because these are tensor in 3 dimensions. And then we know that the atria is represented as a manifold in a 3-dimensional space, so there is no out-of-surface conduction. I mean, the wave can only travel on the atrial surface. And with that, we reduce this from a 3-dimensional tensor to a 2-dimensional tensor. And also we know that D is a positive definite tensor. So with all that in mind, we can compute the conduction velocity tensor like this. So we take the exponential of, so this is the matrix exponential, it's not the component by component exponential of a reduced tensor, D2, which has 3 independent components, so we ensure that it's symmetric. And this matrix P projects this two-dimensional tensor into the three-dimensional tangent plane of the atria. And now, instead of in the previous approach where we only had one output for the neural network, that was the conduction velocity, now our neural network will output 3 quantities, which are D1, D2, and D3. So how we can compute P? So P will be the basis that we use to project the two-dimensional tensor into the atrial surface. And we use a heat vector method, which basically gives us a smooth basis in the manifold. So you can see now here that all these arrows are aligned. So that will make things easier for the neural network, because we are basically predicting conduction velocity tensors in this basis. So if the basis was really irregular, that would be really hard for the neural network. And here we have the structure of the neural network. As before, we have the activation time neural network. So that is unchanged. And we also have a conduction velocity tensor neural network, which outputs D. So lowercase d, which was D1, D2, and D3, that is converted to the uppercase D, which is the tensor in 3 dimensions. And then we compute the loss in of the anisotropic aconal equation, and we also add some regularization terms for the conduction velocity. So here we have some numerical experiments. So this is synthetic data. And here in black, you have the points where that we use for training. And in this example, we also added a scar where the conduction velocity was reduced by half. So these are roughly 800 points. And we use some rule-based fibers for this synthetic example that you will see in a minute. And we train with Adam, which is a very typical neural network optimizer, followed by a step of a second order method, BFGS, to minimize the loss function. And we implemented all this in TensorFlow, so we don't have the gradients are computed automatically. And all the nodes in the mesh are used as collocation points for the aconal residual, but we use batches, so we don't. So this is very efficient. We don't use all the points at every iteration. We only use a small proportion of them. So here are the results. So on the right, you can see the activation times for the reference, and on the left, you can see for the predicted. So you can see that they look really similar, and this was expected because we had a lot of data, and now we are actually more interested in predicting the fibers. So you can see here that there is some slow, the pattern changes, because here is the region where we had the scar, and that is also nicely matched. So we can learn pretty accurately the activation times. And now, if we want to learn the fibers, it performs well, but not as good as for the activation times. So basically, you can see here the color bar means the fiber error. So black will be no error, and white will be 90 degrees of error. So you can see that we can capture most of the structures. So the alignment in this region is pretty good. We can also capture that there is a sudden change in fiber orientation towards where the valves are. And in the opposite view, the results are good, but we have a lot more trouble, especially in the region of the scar. If you remember, the scar was here, and the fiber pattern is actually really complicated here. So we can get some good agreement with the fibers with this method. And actually, if we compare it to previous methods, we see exactly this. So we compare to PyMap, which is a method that is based on a PDA constraint optimization method, where they ensure that the aconal equation is exactly satisfied. And here, and this is our approach, and you can see that we pretty much outperform in most cases for the activation times errors. And in the fiber errors, we are in a really comparable range. So another advantage of our method is that we reduce the computation time from 1 hour to around 25 minutes using 1 GBU. We also did a patient-specific case where we left around 20% of the measurements that a physician did for validation, and we also get a good agreement, and this is actually better than PyMap. So just to finalize, we think that that physics-informed neural networks are a good method to combine data with mathematical models. So in cases where we know how the physics of the problem, we can blend those two information sources very nicely. And we can also, using uncertainty quantification, we can create active learning and recommend the physician where to get the measurements. And we can learn hidden variables that are not directly observable, such as the conduction velocity and the fiber fields. And we can use this approach to many other problems. So the code for the isotropic version is in that link. And some things that we're planning to do with the anisotropic case is to include the uncertainty and the active learning, and also include information from multiple pacing sites to improve the fiber estimation. And that's it. Thank you very much, and I will take questions.
Thank you very much for the presentation. I see that Stefano Pagani has raised his hand, so please, Stefano.
Okay, so thank you very much for your talk. It was really interesting. So I have a curiosity about the framework that we have used in order to describe then in the end the fiber orientation with respect to the free field that you estimated. So you mentioned that you have a starting reference configuration, like a configuration where you have all aligned vectors, and then in some sense you try to estimate the fiber direction, and you constrain to the fact that the propagation should be in a plane. So can you further comment on this aspect, because it was not completely clear for me?
Yes. Yeah, so basically we need to define a basis to project this tensor, so D2, which is a two-dimensional tensor, into 3 dimensions. And for that, we need to create a local reference system in the atria. And that's where this matrix P comes. So we have many ways of doing that. But what makes sense is to use something that is smooth. So for a case where for example, if you wanted to predict a uniform conduction velocity tensor, this will be really easy, because this basis is really smooth and is always pointing in the same direction. If you had sudden changes in this basis, the neural network will have to learn that and basically have discontinuities in the prediction of D1, D2, and D3.
Okay, but this could be seen as, let's say, an a priori information that you could provide about, for example, fiber orientation, or it is completely disconnected from this?
Yeah, I mean, that's a good point. So, I mean, for example, what we could do is, instead of using this smooth basis, we could use a rule-based approach and use that as a basis, and that probably will make things even easier for the neural network. So if you can put as much information here. So in this case, we didn't do that because basically that would be cheating, because in this case the example that we were trying to approximate were created with a rule-based approach. But for example, you're right. I mean, here if we had a basis that already accounted for this discontinuity in fiber direction here, that would probably make things a lot easier for the neural net.
Okay, great. Thank you very much.
No, thank you for the question.
Okay, is there any other question? Okay, I see another raised hand. Please, yeah.
Hi, I had a question about how do you see this being used in the clinic, since it's a little it's still not fully non-invasive. So do you have any plan to make strategies to be used in non-invasive conditions?
So you mean, as long as we can get the activation times, so for example, I would get if you use ECGI, so where they put a vest and they have many electrodes, I guess it should still work because we only need the activation times. So if we had a lot of measurements of activation times, we can certainly apply this approach. But I think before we even get to that, we need to handle a little bit more the uncertainty. I mean, so neural networks tend to give different results pretty much every time you run them. So we need to focus first on sterilize the method a little bit more and quantify the uncertainties, and then we can start thinking of how to translate that into the clinic. But that's a great point.
Thank you.
Okay. So there is another question from the audience. We thank very much the speaker again.